Imagine being able to measure the vastness of the universe from our tiny spot in the cosmos. Imagine a tape measure that doesn't just span cities or countries, but stretches across galaxies and beyond. How do we create and rely on such measurements? The observable universe is estimated to be 93 billion light-years in diameter. That's a number so colossal it's nearly impossible to comprehend. Imagine the vast expanse of space that stretches out before you. It's so enormous that even the speed of light, which travels a mind-bending 186,000 miles every second, would take billions of years to cross it. The scale of our universe is truly awe-inspiring, with distances so vast they challenge our understanding of the world around us. But how do we even begin to comprehend such unfathomable distances? Well, let's put things into perspective. The distance between the Earth and our closest celestial neighbor, the Moon, is about 239,000 miles. Now, if we were to scale that down so that the Earth is the size of a basketball and the Moon a tennis ball, they would be just 24 feet apart. Yet in terms of the universe's scale, this is but a tiny, almost insignificant distance. Now, consider our solar system. If the Sun were the size of that same basketball, the Earth would be a mere peppercorn nearly 26 yards away, while Neptune, the furthest planet, would be nearly 3/4 of a mile away. And our galaxy, the Milky Way? It's so vast that even traveling at light speed, it would take you a staggering 100,000 years to cross it. But remember, our galaxy is just one among an estimated 2 trillion galaxies in the observable universe. The enormity of these numbers is simply staggering. It's a vast cosmic playground that defies comprehension. How then do we even begin to measure such mind-boggling distances? Through a series of ingenious methods and tools, astronomers have been able to map out the universe, giving us a glimpse into the cosmic depths of space. With such mind-boggling distances, one must wonder, how accurate are our measurements of the universe? To measure the universe, astronomers use a cosmic yardstick known as a parsec. Now, you might be wondering, what on earth, or should we say what in the universe, is a parsec? Well, quite simply, a parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond. It's roughly equivalent to 3.26 light-years. So when we say a star is 20 parsecs away, we mean it's a whopping 65.2 light-years from us. But how do we determine this? Enter the concept of parallax. Parallax is the apparent shift in position of an object when viewed from different perspectives. Imagine holding your thumb up and closing one eye, then switching eyes. Notice how your thumb seems to move against the background? That's parallax. Astronomers use this principle on a grander scale. They observe a star from 2 different points in Earth's orbit around the Sun, 6 months apart. The tiny shift in the star's position against the far-off cosmic background gives us the star's parallax. The smaller the parallax, the greater the distance. So we've got this handy cosmic yardstick, the parsec, defined by the parallax of 1 arcsecond, and with it, we measure the unfathomable distances of the universe, from nearby stars to galaxies far, far away. But even with our cosmic yardstick, measuring the universe isn't as straightforward as you might think. Astronomers employ a technique known as the cosmic distance ladder to measure the universe. A pinnacle of human ingenuity, the cosmic distance ladder is a series of interdependent methods, or rungs, that allow us to gauge the enormity of the cosmos. Let's climb this ladder together, shall we? Our first rung is the parallax method. It's akin to winking one eye and then the other to perceive depth. Astronomers use this method to measure distances to nearby stars. They observe a star from 2 different points in Earth's orbit around the Sun and calculate the angle of displacement. With this, they can deduce the star's distance. However, parallax becomes less effective for objects beyond a few hundred light-years as the angles become too small to measure accurately. Ascending to the second rung, we encounter standard candles. These are astronomical objects like certain types of supernovae and variable stars that have known luminosity. By comparing the observed brightness of these celestial bodies with their known luminosity, astronomers can estimate their distance. For instance, Cepheid variable stars have a relationship between their luminosity and pulsation period. This allows us to use them as cosmic yardsticks, even for distances up to millions of light-years. Finally, we reach the top rung of the ladder, redshift. This method is typically used for galaxies that are billions of light-years away. As the universe expands, light from distant galaxies is stretched or redshifted. The more redshifted the light, the farther away the galaxy. By measuring this redshift, astronomers can estimate the galaxy's distance. Each rung's accuracy is dependent on the one below it, creating a cosmic chain of inference, yet the numbers can be mind-boggling. The most distant galaxy ever observed, GNZ 11, is estimated to be about 32 billion light-years away based on its redshift. Yet, despite these intricate methods, there's still a degree of uncertainty in our measurements. As magnificent as the cosmic distance ladder is, it's a reminder that our grasp of the universe is still evolving and there's a whole cosmos out there waiting to be discovered. The Hubble constant, a value that describes the universe's rate of expansion, is currently a subject of heated debate among astronomers. The Hubble constant is a fascinating little number named after the famed astronomer Edwin Hubble. It's a measure of how fast our universe is expanding, a key factor in understanding the age, size, and future fate of the cosmos. But here's the kicker: we can't seem to agree on what it is exactly. There are two primary methods used by scientists to calculate this value. The first approach is a cosmic ground-up method, observing nearby celestial bodies like Cepheid variable stars and supernovae to create a cosmic distance ladder. This method has given us a Hubble constant of about 70 kilometers per second per megaparsec. Now I know that's a mouthful, but bear with me. The second approach is a cosmic top-down method, relying on the cosmic microwave background radiation, the afterglow of the Big Bang. This method gives us a lower Hubble constant of around 67 kilometers per second per megaparsec. Now, you might be thinking, 3 kilometers per second, that's not a big difference, right? Well, in the grand scheme of the universe, this discrepancy is substantial. It's like trying to measure the length of a football field and coming up a few yards short. It doesn't sound like much, but when the stakes are the age and size of the universe, every little bit matters. This discrepancy, often referred to as the Hubble tension, has become one of the most significant controversies in cosmology today. It's a cosmic whodunit, a mystery that's driving scientists to reevaluate our understanding of the universe, pushing them to think outside the box, exploring new physics, and even considering the existence of unknown particles. So, even with our advanced technology and scientific knowledge, our measurements of the universe are still being refined. It's a reminder that our understanding of the cosmos is, like the universe itself, always expanding. Despite the challenges and uncertainties, scientists are ceaselessly working to hone our measurements of the universe. The future of cosmic measurements is as bright as the stars that fill our night sky. New technologies and missions are on the horizon, ready to take our understanding to the next level. One such upcoming mission is the James Webb Space Telescope, set to launch in the near future. This marvel of modern science is expected to provide even more precise measurements of cosmic distances, opening up new frontiers in our understanding of the universe. Then there's the European Space Agency's Euclid mission, designed to probe the dark universe, and NASA's Wide Field Infrared Survey Telescope, which will investigate the nature of dark energy and explore the evolution of galaxies. These missions, along with advancements in technology, are set to revolutionize our cosmic measurements. Think about quantum technologies and how they could dramatically enhance our ability to measure time and distance. Or consider advancements in AI and machine learning, which could help us process astronomical amounts of data more efficiently and accurately. But it's not just about the technology, it's about the people behind it, the scientists, engineers, and researchers who dedicate their lives to exploring the unknown. Their continued efforts are crucial in our quest to understand the universe. So, while our measurements of the universe might not be perfect, they're constantly improving, bringing us ever closer to understanding the vast cosmos.